Hello students and welcome to Chemistry B. I'm Miss Sleight and today we're going to be talking about reactions that occur in aqueous solutions. So by the end of this note set you should be able to write complete and net ionic equations for double replacement reactions, as well as identifying spectator ions within those reactions. Let's begin with a quick review of double replacement reactions. In a double replacement reaction, ions will trade places. So when sodium hydroxide reacts with copper 2 chloride in aqueous solution, your products are going to be sodium chloride and copper 2 hydroxide. To balance this chemical equation, we need a coefficient of 2 on sodium hydroxide and on sodium chloride. And the reason that we know that this combination of chemicals does indeed form a double replacement reaction is because while sodium chloride is an aqueous solution, soluble, copper 2 hydroxide is insoluble and will form a solid precipitate. In order for a double replacement reaction to occur, a solid precipitate must be formed, water must be formed, or a gas must be formed. We're going to start by focusing on reactions that form solid precipitates. So let's say we have aqueous potassium iodide reacting with aqueous silver nitrate. In a double replacement reaction, it will form the products potassium nitrate, which is aqueous, and silver iodide, which is a solid. The question becomes, though, what do these compounds really look like if they're dissolved in a beaker of water? Well, to begin to think about what ionic compounds look like when they're dissolved, we have to know what actually happens in the process of dissolving. So let's take a look at a quick video on that. So what we saw in the video is that the polarity of water molecules will actually break apart the positive and negative ions in ionic compounds that are soluble. So if we were to kind of visualize that for potassium iodide and silver nitrate, if these two compounds were dissolved in a beaker of water, it would kind of look like this, where we can see all of the potassium, iodide, silver, and nitrate ions. They're all spread out and dissolved. However, our products are a little bit different because while potassium nitrate is aqueous, silver iodide is a solid. So the soluble potassium nitrate, those ions will still be broken apart and floating all around in the beaker. But because silver iodide is insoluble, those ions are strongly attracted to each other, and you'll see them forming a solid crystal lattice in the bottom of the beaker. And in fact, we can represent this entire process symbolically. So instead of drawing out the pictures like I did in the beakers previously, now we're just going to write out the symbols for these ions. So our reactants become the potassium +1 ion, the iodine -1 ion, the silver +1 ion, and the nitrate -1 ion, all of which are aqueous. And our products become the potassium +1 ion, the nitrate -1 ion, and solid silver iodide. Again, silver iodide is not separated because it is a solid. And this right here is what we call a complete ionic equation, because it's showing all of the individual ions in the equation as they would exist in that beaker of water. Something that we should notice with a complete ionic equation, however, is that certain ions, like potassium and nitrate, show up on both sides of the equation. Because potassium and nitrate show up on both sides of the equation, they're what we call spectator ions, meaning that they're just watching the reaction take place. They're not actually involved in the chemical reaction. And because those spectator ions aren't actively involved in the reaction, and they exist on both sides of our equation, we can cross them out, just like you would cross out things that are the same on both sides of an algebraic equation. What we're left over with is the iodide ion reacting with the silver ion to form solid silver iodide. This is what we call a net ionic equation. Net ionic equations show just the species that are involved with the chemical reaction. Now let's look at an example of a reaction that will form water. So the balanced chemical equation is aqueous hydrochloric acid reacting with aqueous sodium hydroxide, and the products are liquid water and aqueous sodium chloride. So the first thing we're going to do is we're going to write the complete ionic equation, separating the ions of everything that's aqueous. Anything that's not aqueous does not get separated. So as we can see in the reactants, all of the ions are separated because both of our reactant compounds are aqueous. However, in the products, only sodium chloride is separated into its ions because it's aqueous. Water remains as H2O because it is a liquid. So this is the complete ionic equation, all of the ions involved in the reaction. Now what we need to do is identify the spectator ions, which ions are the same on both sides, and cross them out to write the net ionic equation. Chloride and sodium are spectator ions. So when we write our net ionic equation, we have the hydrogen ion reacting with the hydroxide ion to form liquid water. Lastly, let's look at a reaction that forms a gas. The balanced chemical equation is sulfuric acid reacting with 2 formula units of aqueous sodium cyanide, and that produces 2 molecules of hydrogen cyanide gas and aqueous sodium sulfate. So I'd like you to take a moment and pause the video and try writing the complete ionic equation and net ionic equation for this reaction. All right, let's see how you did. In our reactants, both compounds are aqueous, so they should all be separated into their ions. So we should have 2 hydrogen ions because it's H2SO4, 1 sulfate ion, 2 sodium ions, and 2 cyanide ions. In the products, hydrogen cyanide is a gas, so it's going to remain as its molecule, but sodium sulfate is aqueous, so we're going to separate that into its ions. To write the net ionic equation, we should notice that sulfate and sodium are the same on both sides of the reaction. So our net ionic equation is the hydrogen ion reacting with the cyanide ion to form hydrogen cyanide gas. And that's how you write complete and net ionic equations for double replacement reactions. Take care and have a great rest of your day.